So here we want to show you that why the sample mean and sample variance are good point estimator, right? And we haven't often mentioned that, but we try to explain why and why the sample variance use n minus 1, right, instead of the population divided by n. Okay, that is beside that is fit our t distribution, right? But uh, but we try to understand why that is a good thing. So we call last chapter the sample mean and sample variance, the sum sample observation that is called the sample means average the observation. Sample variance is the difference of each observation per mean and square the difference, and sum of them divided by n minus 1. So this n minus 1 here. So now we try to explain. Okay. First, sample mean, okay, is unbiased. Okay, is easily we have shown this, right? Because in last chapter, because of summation of xi over n, then you can easily show this is mu. Okay, and but actually this is true for any linear combination of estimator, right? It need not be sum, right? Can be 3 of x1 plus 2 of x3 and so on and so forth. Any weighted average will be fine. Okay. But why sample mean is good, right? We need to explain. So let's try to show, okay, among any linear combination, actually the mean is the best. Okay. That means the weighted average of the weights are 1 over n equal weighted is the best. Okay. Why? Okay. Look at the variance. It's the most efficient one. Okay. So variance of this any kind of combination, right? Because this is independent, right? So that's why there's no covariance. You can take this out. Okay? You can take the sigma out. Okay, summation. You can take the sigma square out, and we can rewrite this because it's drawing from the random sample to sigma square. Okay, sigma square can be taken out. So which is sum of this weight square, and this by Cauchy-Schwarz inequality, okay, is greater or equal to 1 over n. Okay, and to prove this we need Cauchy-Schwarz inequality. But anyway, it's not important. I mean, so that means that 1 over n is the minimum variance. So that's why that's how you prove it. So why sample variance? Sample variance is 1 over n minus 1 instead of 1 over n because this is unbiased estimator. Okay, we will show s squared is equal to sigma rather than if you use n minus 1 instead of n. So this is how we prove it. Okay, so what we know s squared is 1 over n minus 1 times this guy, right? So that's we can take a 1 over n minus 1, okay? And this summation sign, we can just expand it, right? So expand the square will be xi squared minus 2 bar xi and x bar squared, right? And because the summation, right, xi, and because we just don't write the I because they're the same for everything. So this same as nx bar x squared minus 2n x bar because summation of xi x, right, can be written n x bar. Okay, and this is x bar squared. Okay, that should be to be plus, so it should be n x bar squared. Okay, and minus 2n plus n become 1n, so that's typo here is plus n. Okay, take out the n, right? Then what we have is n over n minus 1, expect the x squared minus e to the x bar squared. Okay, so the only thing we don't know is this guy. Okay, need to know this one. So expect the x bar squared, okay, is equal to, write down the expression, right? X bar is sum of the xi over n, okay? And then you just expand it, right? Because this is 1 over n can be taken out is x1 up to xn times 1 over xn, right? So time itself, right? You have x1 square, x2 square, x3 square add up together. Here I also have a bunch of I not equal to j, right? x1 times x2, x2 times x1, x2 times x3. So this is a bunch of those, okay? Not equal to each other. And actually this means we have n of the x square, right? And this is we have n times n minus 1, okay, because they're not the same, right? Look at the two-way table, right? Is n square minus n, right, will be n times n minus 1, okay? They're multiplying, right? So it's expected the product of it, right? Because why this is the case? Because they're independent, right? So that's why this is the case. And the n we cancel out, right? So that's what you left here, okay? Now take it back, okay? S squared, okay, is this guy, right? So replace this guy with what we have shown, okay? And there's no more x bar, right? So basically x squared. So and then you can see, right? This n minus 1 will cancel out, and n minus 1 will cancel out. So what left is this guy, and this guy is exactly the sigma square. So that's how you prove this unbiasedness. Okay, so same for proportion. Proportion is a special case for the sample mean. So the sample average and sample variance is a unbiased estimator of the what we want to estimate. Okay.